Hello everyone. In this video we are going to discuss Bernoulli's equation. Bernoulli's equation describes the flow of liquid through a pipe, a non-uniform pipe, which have different cross-section area at different regions. The flow of liquid through the pipe is dictated by the elevation of the pipe at different regions and the pressure. As the liquid is flowing through the pipe, it means that there are certain pressures at different regions which dictate the flow of liquid. So, we are going to study the effect of the pressure at different regions and the elevation of the pipe on the fluid flow. This is a pipe of different cross section area at different region. At end A, we have a cross section area AA, and at end B, we have a cross section area AB, and the liquid is flowing through it. The flow is streamlined. That is, the trajectories of particles of liquid will not intersect each other. The velocity of liquid particle at any point at any particular point on a trajectory will be same for all the particles. Means whichever particle of the liquid happens to be at a certain point on a trajectory, it will have the same velocity there. This is the streamline flow. Now we shall try to understand the flow of liquid by dividing the liquid into a large number of small subsections, and we describe the flow of liquid in a way that each subsection replaces the next subsection as the liquid flow. These subsections are shown in this diagram. This is the first subsection, this is the second subsection, this is the third, and so on. There are such n subsections. So, as the fluid flow, as the liquid flow, the first subsection will replace the second subsection will replace the third, and so on. Moreover, these subsections are so small that we can assume their velocity to be same throughout their volume. As the liquid flow from left to the right through this pipe, there is a certain pressure at this end. The pressure exerted by the liquid outside the end A of the pipe. There is a certain mass of liquid we have considered with the volume VA. This mass of the liquid will push onto the liquid inside the pipe, and that push create the pressure PA at this end of the pipe. So, because of this pressure, the liquid will be pushed through the pipe, and as the liquid is pushed through the pipe, the liquid inside the pipe as it flows also pushes onto the liquid that is present outside the end B. So, as the liquid is pushed from the left end A of the pipe, there is some work done on the liquid inside the pipe, and the liquid inside the pipe in turn pushes onto the liquid that is outside the another end B of the pipe, and in pushing that liquid which is outside, the liquid inside the pipe is doing work on the outside liquid. So, here the work is happening in two ways. The work is done onto the liquid mass inside the pipe from the left end, and the work is done by the liquid onto the liquid outside the pipe at the end B. So, as a result of these works, there are energy changes happening inside this liquid mass. We are describing the flow of liquid as the replacement of one subsection of the liquid by its previous subsection. It means this is the subsection number 1, subsection number 2, number 3, 4, and so on. So, the subsection 1 will replace the 2, the subsection 2 will replace the 3, and so on. And all these subsections are flowing with their own speed of flow. So, the subsection 1 can be considered to have a speed V1, the subsection 2 has the speed V2, subsection 3 has V3, and so on. So, in time delta t or in time dt, the subsection 1 moves and replaces the subsection 2. The subsection 2 moves further and it replaces the subsection 3, and so on. The volumes of all these subsections are equal because they are supposed to replace each other and the mass of the liquid remains same and the liquid is incompressible. So, because of the incompressibility of the liquid and because the total mass is conserved, the subsection 1 on replacing the subsection 2, it has to have the same mass when it replaces the subsection 2, and subsection 2 on replacing the subsection 3, it is also supposed to have the same mass contained in the region of subsection 3. So in in this picture of liquid flow where the subsections are replaced by the previous subsections, all the subsections must have same volume and hence the same mass because the density of the liquid is same. So, in time dt, the first subsection has moved forward and it has replaced the subsection 2 has replaced the subsection 3 and so on. And the equal amount of liquid mass that is present outside the pipe, which is shown by green color here, that green color liquid mass which has the same volume as the volumes of this subsection will completely enter the pipe, and when this so happen, the equal amount of liquid must emerge from the other end of the pipe. So whatever amount of liquid enter, the same amount of liquid must emerge from the other end of the pipe, and this must happen because the liquid is incompressible and the mass of the liquid is conserved. So after the time dt, when the liquid has flown through the pipe, the liquid mass that was outside has completely entered into the pipe and same amount of liquid has emerged out from the other end of the pipe, same volume. The liquid flow through the pipe is controlled by mainly two parameters. One is the pressure onto the ends of this pipe, from the liquid outside it. So here is some pressure due to the liquid that is flowing into the pipe, and here is also the pressure onto the liquid inside the pipe due to the liquid that is present outside. So this pressure pushes the liquid inside the pipe towards the right, but that flow of the liquid towards the right is opposed by the pressure due to the liquid that is present outside the pipe at the end B. So these pressures and also the force of gravity dictate the flow of liquid through it, and we are going to find the effect of gravity and these pressures at different regions of the pipe on the liquid flow. Okay, so let's suppose that the first subsection, let's call this subsection the liquid element. So first liquid element has the velocity v1, the second has the velocity v2, the third has the velocity v3, or the v4 and so on. So these different liquid elements have different flow speeds. And when one subsection or one liquid element, for example, if the liquid element 3 replaces the liquid element 4, because of the streamline flow, the liquid element 3 will have the velocity of liquid element 4. So whatever the velocity the liquid element 4 had before, the same velocity this liquid will be gained by the liquid element 3 when it replaces the liquid element 4. That is the characteristic of streamline flow. In streamline flow, whichever the point on trajectory we consider, whenever a particle of liquid arrive at that point, it will have the same velocity as the other particles which pass through that point. The first element of liquid, let's call the first element of liquid, the velocity of first element of liquid as nu A to indicate that this is the first element of liquid and it is at the end A of the pipe. Similarly, the liquid element at the end B of the pipe, let's say have this liquid element the velocity Vb. We have divided the liquid mass in the pipe into n liquid elements. All of them have same volume and same mass. So the nu b represent the velocity of this last liquid element Vn, and nu A is equal to nu1, the velocity of the first liquid element. The pressure at end A of the pipe pushes the liquid through the pipe, and that pressure causes a force on the liquid which displaces the liquid through a displacement, say dx. as shown in this following diagram. The force Fa displaces the liquid through the distance dx, and the equal volume of the liquid emerges from the other end of the pipe, and there the displacement of the liquid is dxb. This displacement occurs against the force from the pressure due to the liquid outside the end B. We are viewing the liquid flow as the replacement of liquid elements by the previous liquid element. So, as the liquid elements advances further, the flow speed also changes. The flow speed changes means there are changes in the kinetic energy of those liquid elements. Moreover, the elevation of liquid elements do also change, and therefore there is a change in their potential energy. The changes in kinetic energy and potential energy are brought about by the work that is done on the liquid mass inside the pipe due to the forces from end A, and the work done by the liquid mass against the forces due to the liquid present outside the end B. So, the work is done on the liquid as well as some work is done by the liquid. So, as a result of this work, there are changes in kinetic and potential energy of these liquid elements, and hence of the entire liquid mass. The work W done during the liquid flow for the time dt consists of the work done onto the liquid mass by the force Fa at the end A, and the work done by the liquid mass against the force Fb at the end B. It is shown in this diagram. The force Fb is against the direction of liquid flow. So we calculate the total work done W. The total work done is equal to the sum of works done on individual liquid elements. So the work done on the first liquid element work done on the first liquid element, work done on the second liquid element, work done on the third liquid element. In this way, the work done on all the liquid elements will be added and it will give us the total work done in the process. So, work done on the first liquid element. The first liquid element has been displaced through a distance dx by the force Fa as shown in this diagram, and the liquid mass that was before outside the end A of the pipe, it has fully entered into the pipe, and the same volume of the liquid is forced out from the other end of the pipe. So, the first liquid element has undergone the displacement of dxa due to the force Fa. So, work done on it is Fa multiplied by dxa. We note here that the force and displacement are in the same direction and it is true for all the liquid elements. Now, the liquid element 2, liquid element 3 and all the liquid element up to uh, liquid element n minus 1, actually there are n liquid elements. So, from the liquid element 2 to liquid element n minus 1, 2 to n minus 1. The works done on these liquid elements are uh, performed by the internal forces. The works on these liquid elements from 2 to n minus 1, these works are actually performed by internal forces, the forces between the liquid elements as they presses onto each other during liquid flow. And these internal forces between the liquid elements follow Newton's second law of motion. These forces are equal and opposite. So these forces are equal and opposite. The one liquid element moves in the direction of the force while the other liquid element moves in the opposite direction of the internal force. And we know about this well because all the liquid elements are moving in the one direction. So whenever for example here we take these two liquid elements, this liquid element exert a force in this direction onto the second liquid element, and the second liquid element exert a force in the opposite direction, while the two elements are both moving in the same direction, which is towards the right. So the work done by this force is positive, while the work done by this force will be negative because this force is in the opposite direction to the displacement that occur. So these equal and opposite forces causes the causes the displacement. It causes the displacement in the same direction, but because the forces are opposite and displacements are in the same direction, the two works done will be equal in magnitude but opposite in sign. So here we see that the works done by these internal forces cancel out in pair, and only the works done on the first liquid element by the force Fa and the work done on the last liquid element against the force Fb as shown in this diagram. Only these work done will be non-vanishing, while the work done on all the liquid elements from 2 to n minus 1 means all the liquid elements which are in between the first and last liquid element, work done on them will vanish. Those work done, this is the work done on the first liquid element by the external force Fa, and we sum the work done on all the liquid elements in between these end liquid elements, means liquid elements 2 to n minus 1. The work done on them we denote it by Wi and call it the internal work done. And then the work done uh, at the last liquid element. The last liquid element, nth liquid element, is actually moving against the external force AB. So here the work done will be negative. As already discussed, this internal work or the works on the liquid elements due to internal forces, this work altogether vanish because the work done on the internal forces, the work due to the internal forces cancel out pairwise. So we have work equal to Fa dxa minus Ab dxb. So this is the total work done in the process where the liquid, entire mass of the liquid inside the pipe has been flown for a time dt. Now this work done results into the change in kinetic and potential energy of these individual liquid elements and hence of the entire liquid mass inside the pipe. We first calculate the kinetic energy gain by different liquid elements. The first liquid element move and replaces the second liquid element. Here we show it. The first element replaces the second element replaces the third. And in this process, the first element, the speed of the flow speed of the first element changes to the speed of the second element. Means the speed of the first liquid element changes from Va to V2, and therefore the change in kinetic energy of the first element is it is half m V2 square minus Va square. This is the change in kinetic energy of the first element. Second element moves and replaces the third element, and it acquires the speed of third element. So change in kinetic energy for the second element will be half m V3 square minus V2 square. We can continue like this for all the liquid elements and finally arrive at the last liquid element whose change in kinetic energy will be half m Vb square minus Va square, sorry, Vn minus 1 square. Note that the speed Va represents the flow speed of the first element. So it is actually the flow speed at end A of the pipe, and similarly Vb that represents the flow speed of the last liquid element on emerging the pipe. So it is the flow speed at the end B of the pipe. So note that V2 square is positive here and negative here, so they cancel out. Similarly, V3 square will cancel, V4 square will cancel, and only the Vb square will remain because there is no there is no other term in which Vb square would cancel. Vn minus square term is present in the previous term with a positive sign. So Vn minus square term will cancel with the positive value in the previous term. So all the velocities cancels except the velocity Va square and Vb square, and we get the kinetic energy gain by the entire liquid mass as half m Vb square minus half m Va square. Note that the masses of all the liquid elements are equal because the liquid elements are just replacing each other, and they are incompressible and they have same mass. So if the second element is to be replaced by the first element, it means the same mass must occupy the volume of the second liquid element, because the liquid is not compressible and mass must be conserved. Now we calculate the potential energies gained by various liquid elements and add them. The potential energy simply correspond to their elevation, how high they have been lifted. That gives the potential energy. So we calculate potential energy for the first liquid element. Uh, Suppose that the end A of the pipe has the elevation y1, and end B of the pipe has the elevation yn equal to yb and y1 equal to ya. And similarly, the elevations of other liquid elements may be may be shown as y2, y3, y4, and so on. So when the first liquid element has moved forward and has replaced the second liquid element, it is now at the elevation of y2. The elevations may be shown here. The elevation is ya, the elevation of the second element y2, of third element y3 from a certain reference level. So when first element has moved and replaced the second element, its elevation has changed from Ya to Y2. So its potential energy change will be mg multiplied by the elevation through which the liquid has rise, and this will be Y2 minus Ya. The second liquid element replaces the third liquid element, and it undergoes the elevation from Y2 to Y3. So potential energy will be Y3 minus Y2. Y3 minus Y2 represent how high it has risen. Similarly, for the third element, we have the potential energy equal to Y4 minus Y3. It has risen to the level of fourth liquid element. So the rise is Y4 minus Y3. We continue like this and reach the final liquid element, which has risen from the level of yn minus 1 to the level of yb. So its elevation will be yb minus yn minus 1. Potential energy is m. Here also similar cancellation occur. Y2 is negative here, Y2 is positive here. Similarly, Y3 negative here, Y3 positive here. So in this way cancellation occur, and only two elevations survive. One is Ya, another is Yb. This Yn minus 1 will cancel with the Yn minus 1 in the previous term, which I have not shown. So finally, after making all these cancellations, we get the potential energy change for the whole liquid mass as mg into yb minus ya. These changes in potential energy and kinetic energy have occurred because of the work done on the entire liquid mass, which we have calculated here. The work done is equal to, so this work done is equal to change in the energy of the entire liquid mass, and change in energy is partly in kinetic energy and partly in potential energy. So we write work done onto the liquid mass is equal to the change in kinetic energy plus the change in potential energy, which we have already calculated. Now we make substitutions for them. We have already calculated kinetic energy change is half mvb square minus half mva square plus the change in potential energy is mg yb minus ya, and the work done, we substitute for work fa dxa minus fb dxb. So we have fa dxa minus fb dxb equal to, Now the force Fa at the end A of the pipe, it may be written as pressure multiplied by area of that cross section of the pipe, and then it is dxa, minus the force Ab is pressure at the end B into the area of cross section of the end B, then dxb. Now this area of cross section multiplied by the displacement dxa, it represents the volume of liquid mass, because our liquid elements are cylindrical in shape. So displacement represents the height of the cylinder, and the area of cross section is the base area of that cylindrical shape of liquid element. So base area multiplied by height gives us the volume of liquid element, the liquid element that is at the end A. So we write it as Pa into the volume of the liquid element at end A. Similarly, Pb into Vb equal to half. We write mass as density multiplied by volume. Density is rho, and the volume of the liquid element at B is Vb, and Ub square minus half rho Va mu A square. Now the volume Va of the first liquid element and the volume Vb of the last liquid element, they must be equal, because whatever amount of liquid which has flown forward, the same amount of liquid must emerge outside the pipe. So Vb is actually the volume of the last element which has emerged outside, and Va is the volume of the first liquid element which has moved forward into the pipe, and the same amount of volume of liquid, same amount of liquid outside the pipe has replace the first liquid element here. So the volumes of basically all the liquid elements must be same, because they are just different liquid elements are just replacing each other with the constant density and constant mass. So Va is equal to Vb. So when this is so, all the volumes Va, Vb from the two sides of the equation will cancel, and we will get Pa minus Pb equal half rho nu b square minus half. Now we take the quantities which correspond to n A on one side and the quantities corresponding to n B on the other side, and we get this equation by rearranging this equation. Look at this equation and we see that the sum of three quantities, the pressure, the rho B A square and rho G by A, the pressure of the sum of these quantities at n A and at n B is same, and the two ends that we have considered are completely arbitrary. So take any two ends or two sections of the pipe and you calculate the sum of these three quantities at those two sections of the pipe, and they will have the same value. That is, at every cross section of the pipe we have a constant value for sum of these three quantities, and that is what the Bernoulli equation is. That is, the sum of the quantities, the pressure P at a particular cross section of the pipe, the value of this quantity, the density multiplied by flow speed square, plus plus rho G y, it is equal to constant. This equation states that at any particular cross section of the pipe, the sum of the pressure at that cross section, the rho multiplied by flow speed square plus rho Gy, where y is the elevation of that particular section, the sum of these three quantities is constant. And there are quite astounding implications of this equation, the Bernoulli equation. So this is finally the Bernoulli equation, and this Bernoulli equation, as one of the main implication of the Bernoulli equation, here we see that at region where the flow speed is high, the pressure must be small, so that the sum remain constant, and the region where the flow speed is smaller, the pressure must be high. It is quite against our normal experience or our intuition. We tend to think that wherever the speed is high, speed flow or speed is high, the pressure must be high there. Or wherever the flow speed is low, the pressure must be high there. But this is not so. Wherever the flow speed is high, the pressure is low there, and wherever the flow speed is low, the pressure is high. So it is against our intuition. It is against our normal experience. So, for example, uh, in stormy weather, the air flowing from the top of the roof, it has a very high speed, while the air inside the room has low speed. So because of the high speed flow of air above the top, there is a low pressure created there above the roof, and below the roof, where the airflow is very airflow speed is very small below the roof. So pressure there is high. So pressure below the roof is higher, and pressure above the roof, here pressure above the roof is lower, and the pressure below the roof is higher. So this creates a net pressure in the upward direction, and the roofs are blown away. So this is just one of the implications of the Bernoulli equation. We stop here. Thank you.